Hey guys. All right, so now that my brain fog is hopefully over and done with, I wanted to make sure I explained to you about the lab and the graph so that you understood how to do it. Even though I only want one per team, I still want everybody to understand what it means. And so I apologize for the total brain fog. I've never been great with math because I have a learning disability in math and I lose confidence easily. But aside from that, like I was telling you guys, I've had like some bad autoimmune flare week. So my brain just occasionally checks out. It checked out when everybody started asking me math questions, and I kind of felt like a moron. So I want to explain it to you all. So I'm going to share my screen, and I'm going to show you what I've got here. Okay. All right, so let me get that out of the way. First things first, here is what the lab said it wanted us to do. All right, right here under graphing, it says you need to construct a graph for acceleration of the car. So what we're going to represent in the graph here is the acceleration. Okay, that's what the graph is supposed to show at different angles of the incline. So if you're going to represent the acceleration at different angles, then you have to show how the car accelerates for one angle and another, and then the third. Okay, it should be a line graph. Got it? And place the time values. Look at this. This is also where my brain checked out. Values for the car. Okay, this is plural and this is singular. So that means we want more than one time value per car. Keep that in your mind. On the x-axis, remember that's the horizontal one, and the velocity values on the y-axis. Values, again, okay, so we're looking for plural values. Okay, and then it says exact same thing for the marble. So here's what I did. I did a mock-up for you, and it looks like this. All right, here we go. And this is going to be, kind of move that out of the way. Can't make it any smaller. All right, so here's what we have. We have our rolling car. This is your example. So this is our formula for average right here. So this means average equals sigma x n. So what that means is exactly this. You take all of the different values, that's sigma x, sigma means sum of the values, and you divide it by n, which is the number of values. I think most of you all understood this part. So for our 10-degree angle, these were some mock-up time trial numbers, okay? And we had 3 different times divided by the number of times, that's 3, okay? And we came up with this equation here, 4.15 divided by 3. So our average time was 1.38 seconds. And then moving down, you can see we have average times for 25 and 40-degree inclines as well. Distance of the inclined plane was the same in all cases, okay? So this is our t value, these 3 numbers, and this is our d value, this identical number all the way through. And, oh, can I move that? You can't see what I did. Can I see? Oh, that's better. Let me move my face out of your way. Here's acceleration for you. Well, let's do velocity first. So velocity here is distance over time. Your distance is the same in every case. Here's your time. This is where we got that number from right here and brought it to here, okay? So when we go ahead and divide the distance by each of the different times that correspond with each of the different incline angles, you get a velocity value. And we went with 2 significant digits here past your decimal because that's just a good solid rule. We'll go with that. So that is centimeters per second, because here's your centimeters, here's your seconds, and you divided your centimeters by your seconds. So here it's the same thing, centimeters over seconds. This could be like divided by or per. Okay, got that? Got that. As long as we're all together here. All right, here's acceleration. Delta V over delta T. So that's your change in velocity over your change in time. Okay, so to get your change in velocity or your delta velocity, you have to have your final, that's the little f, and can I make it bigger? Yep, your little f and your little v. Okay? I mean your little I. That's initial. So final, initial. So here's where we started. Here's our final, for example. Here it is. We got it right here. And remember, we got that by dividing this number by this number. Okay. So it's 42.43 centimeters per second minus 0. Why is it 0? Because it's 0 is where we started. There was no acceleration when the car was stopped at the beginning, right? If it's stopped, it's not moving. So we divide that, we subtract that and divide it by the time, because acceleration is your change in time. So here's your final time, 1.38, and your initial time is 0. Again, we started the clock when it moved. So basically, here's your value for this, and this is your acceleration. It's 23.57 meters per second squared. That should say centimeters. Darn it. Ignore those meters. They should all say centimeter. I will correct that and send this out in an email. So they should all say centimeters per second squared. See, and when I copied them here, I did it again. Oh, this only took me like 2 hours to make and make neat for you people. Anyway, so remember that it's supposed to be centimeters per second squared, because you've got these here and then here, and you end up with an extra. Anyway, we've been over this. All right, so we come down here. So here's how we plot the graph. It said, if you remember back here, to plot the time values. So, and then it also says the velocity values. So what is that? Here is the time values are right here, and the velocity values are right here. They're both two values, started at 0. So we're going to take our purple one here. That's our 10 degree. We started at 0, and we went to 23.57, and that's where we plot it, and it makes a nice straight line because it is accelerating in a positive direction. Same thing here. We take our velocity, our change in velocity over our change in time, started at 0. There's where we ended up right there. That's 58.82. Okay, nice straight line, accelerating positively. And look at, here's the green one, same thing. We'll look at our 40-degree incline, which is our green one this whole way through here. Look how nice and tall that is. You can see that it's got a greater slope because it has a greater acceleration. Okay, so how do you calculate the acceleration using a graph? You do rise over run. So looky here. Here's our rise right there for purple. And what is it? Oh, what do you know? It's 42.43. Where have we seen that before? Right here. And there it is. We're going to plug it in. And what's our run? Oh, look, there's our run. 1.4, or roughly 1.4, so 1.38, and there it is. What do you know? And this number is this number. It's exactly the same. So this graph represents this chart. So you can see the acceleration here. You can read this all day long, and it doesn't mean as much to you as looking at the difference between the slopes. Okay, so I'm going to go and I'm going to change my meters to centimeters, because that's going to make me insane if I don't do that. Gosh, man, I'm telling you, it has been a long day. And now I'm going to have to adjust the spacing, because look at that, y'all. Okay, so I'm going to send this out. And I just want to make sure that you guys understood it, because that was not necessarily clear today in class since my brain checked out. So I will see you guys next week. And if you have other questions, where's my thing? Oh, no, not that. Oh, my goodness. Look at this, look at this, look at this. Aye. So anyway, if you have other questions, let me know. Otherwise, you should be good to go. Just one graph per team. That's how your graph should look. Now, Michael, you handed in your lab already, and I think you had the data for your whole team, but this graph bit wasn't clear. So I'm going to take a picture of your data and send it back to you, and if you can just graph it out and fill in the chart again. Awesome. All right. See you guys next week. Later.